Okay, good afternoon. Is that too loud? Should I move it down? So I'm Mark Moldwin, professor of space sciences and engineering, and from the University of Michigan. And for the next two little mini 45-minute sections, I hope to have you guys thinking and maybe meeting somebody next to you or behind you as we start thinking about processes in astrophysics, heliophysics, space physics. And one of the interesting aspects of the space sciences, NASA divides the space sciences up into different domains. And you can sort of think about astrophysics as studying things outside the solar system and space physics inside the solar system. The other difference is astrophysics is looking at photons from far away, where space physicists can build robots to go places. It's, of course, we both use remote sensing, so there's a lot of overlap. And it was great to have the 30 to 60-second introductions to everybody's background. And one of the things you probably noticed is that you guys have a lot of different backgrounds. And that's kind of unique to the heliophysics or space physics field, and it's because it's a young field. It essentially got its roots out of a number of different disciplines. So a lot of the early cosmic ray physicists were in physics departments. A lot of the ionospheric people were doing radar, so they come out of electrical engineering departments. A lot of the geomagnetism folks got their roots out of geophysics departments. A lot of the upper atmosphere people came out of geoscience, atmospheric type of departments. Right? And a lot of the remote sensing people came out of astronomy departments. And so that's the way we are. So you could have your PhD in astronomy, in physics, in electrical engineering, in geophysics, or atmospheric physics, or whatnot. But we all solve the same problem. But we all have that little framework of our training. So if you're an electrical engineer, you think differently than a physicist. You think differently than a geoscientist. You think differently than a mathematician. And so one of the things we'd like you to get out of this workshop is there's advantages of thinking differently than the way you were trained. And so meet everybody here, and they're going to have different frameworks. There's going to be people doing MHD, and there's going to be people doing particles. There's going to be people talking about current sheets and magnetospheres or astrospheres, or exoplanets, counting photons, spectroscopy, all of them. We see the universe in a different way. But most of the problems are going to be at that intersection of disciplines. You need to understand the instrument. You need to understand the physics. You need to understand the uncertainties and the assumptions. So what I'd like you to do for this afternoon is try to think differently. And I now know your background. And if you're not too talkative, I do have your names. And I also know a little bit about you. But think about heliophysics. You obviously signed up for a heliophysics summer school. Would you be able to stand up and give a 30-second definition of what heliophysics is? But I want it in terms of domains. So regions or places. Would you be able to divide it up? Anybody want to take a stab? How about 1, 2, 3? Oh, we'll have you just. I can do it, but I'm too embarrassed to stand up. I think I know it, and if you ask me to tell my neighbor, I would tell him, or I have no idea. I never heard of heliophysics as a discipline before. So pull out your clickers and tell me which one, 1, 2, or 3. So we have mostly 1s and 2s. Okay. That's one way we divide up the universe or anything is by domains. So I could be a physician and I study the human body. And if you met a doctor, you might ask, what's your specialty? And they might tell you, you're a throat or an oncologist or whatever, right? Some type of discipline. But I also can think of the human body as a whole bunch of systems, right? So it's a complex system, and I can study the circulatory system or the respiratory system or the nervous system or the muscular system or whatever, right? And of course, when you go through med school, you're going to learn about all of those, but a good physician is somebody who understands the interconnections between your diet and your exercise and whatnot. So that's the same thing for you. Hopefully all of you are going to be PhDs or are PhDs in space science and don't see yourself as a cosmic ray physicist or a solar physicist. You are a space physicist and you can look at all of those domains and see what their similarities and differences are. Okay, just raise your hand. I've taken a graduate level space plasma physics course. So pretty much a good little bit over half. How many of you have undergraduate degree in physics? So most of you. And that's kind of interesting is that when you think about any of these applied disciplines, the geosciences, the geophysicists, we often come from the traditional disciplines because that's what academia has been doing for over 100 years. We have physics departments and chemistry departments. We have biology departments. And then you go ask somebody and they go, oh, I'm a biogeochemical microbiologist, right? I mean, that's what we're doing. We're trying to figure out. And so where did you get your training is going to tell you how you think. So if you came out of a biology undergraduate degree and then did some type of exobiology, you might be thinking very differently than if you came out of physics. So understand that we have our biases because of our training. And one of the biases of physicists, which I like, and the reason why I went into physics is we like to simplify things. And so that's one of my goals for today is to get you to think as simply as possible as you develop your framework of understanding of the heliophysics. How many of you have read the heliophysics text? All of them, you got them mailed to you, right? Anybody open them? Have a name in them? Go through the table of contents? If it was a PDF, you would have read it, or if it was an iBook, but since it's a physical book, I'm not going to bring it with me. So there's a copy. So obviously, one of the biases of the faculty here is that we wrote those chapters, and so we expect you to have read them. But of course, the bias of a student is I have so much other things to do that I'm hoping to get it from these lectures. Why would I come? But if you can take yourself back, we spent a lot of time writing these chapters. There was a lot of thought, a lot of collaboration. Carol was a great editor, and George Sisko. And yeah. And so that thought about what would be the best order. What are some of the fundamental concepts? How should we divide up the textbook? How should we organize it? So if nothing, you should take a look at what's the difference between Volume 1, Volume 2, Volume 3. Are there any similarities? Can I see something over and over again in each of those books? And if you do, that's probably an important topic. And you should be a very good self-assessor. This is what I'm strong in, this is what I'm weak in, and this is an important concept and I'm weak in it. Maybe you should take some time. You have a whole week here to ask a whole bunch of faculty. And so unlike a university where you generally have one professor of a classroom, you have a lot of faculty and yourselves. There's a lot of PhDs in the audience too. We have a lot of postdocs, and you're all senior grad students. So take advantage of your environment. Okay. So physicists are different than other scientists because we like to simplify. Biologists will look at a spider and say there's an extra hair behind the third leg and therefore it's a new species and therefore I need to do a DNA. A physicist, it's a spider, right? Lightning and a static electric spark are the same thing, right? We like to, what is it in essence? What are we looking at? And so when you think about organizing the field of heliophysics, there's essentially two different ways that people take this complex coupled system and try to put order to it. And one is this idea of structure. I'm a solar physicist. I'm a solar wind physicist. I'm a magnetospheric physicist. I'm an ionospheric physicist. I'm an upper atmospheric physicist. And I can actually tell you exactly where it is. It's from 100 kilometers to 1,000 kilometers, or it's out to 10 Earth radii, or whatnot, right? I have a place. And a lot of textbooks are organized. We're going to have a tour of the solar system. We might go from the sun to Mercury, whatnot, and we'll stop each way. And just like an anthropologist looking at ancient civilizations, we'll talk about the similarities. What language did they use? What did they eat? What type of commerce? Right? Why did they go away? The same thing for us. What's the similarities between Mercury and Mars? What are the differences between Venus and Earth? And so we start asking these compare and contrast questions. Why are they the same? Why are they different? The other thing we're interested in is the d by dt. We're interested in changes, dynamics. Why is there a mass loss of Mars? Where did the N go, or the rho go, or the H go, or the water go? We want to know. We want to understand dN H2O dt, not only over the time of a EUV flare, but over a solar cycle, and even over the multi-billion year lifetime of the atmosphere. Where did it go? And so we have to start thinking about the processes of that continuity equation. What are the sources and the losses that give rise to changes in this? Or is it just purely transport? All of it went into the ice, right? So we can start arguing about it. The other way we can divide up a textbook, and what I'll be talking about this afternoon, is processes. And these are the universal physics of all the disciplines. You can sort of think about, I can write F equals ma for a lot of different systems. If I'm interested in the dynamics or the structure of something, what forces created the Grand Canyon? What forces make a magnetosphere a blunt windsock type object? What makes Jupiter's magnetosphere a different size structure than the Earth's magnetosphere, right? I can ask all these questions, and it's the same equation. And so if I understand what that equation was, what that process is, I can just start doing comparative planetology. I can start thinking of a star just like a planet in terms of a magnetosphere. But of course, then I want to compare and contrast. Why is the stellar corona different than the Mars exosphere? What processes are different? So as we go through this week plus, start thinking of those similarities and the differences. We're going to be doing this big tour, but could you write down just the name of, momentum equation, continuity equation? Here, source is important. Here's loss is important. Here, electromagnetic forces are important. Here, pressure gradients are important, right? Where do you get that? And how do you make that decision? What's important or not? What would you ask yourself? I can neglect this term, or I can make an assumption and just set this equal to 0. And so that's hopefully one of your goals as a learned person, is organizing your thoughts. And generally we can tell the quality of your thinking by the way you organize your thoughts. And so if you haven't thought about how you organize your thoughts, how do you put some simple model together or a conceptual framework to figure out when one thing is important or not? If you haven't thought about it consciously, you should start thinking about, if I had to write down a one-page essay on whatever topic, how would I organize that essay? What would I put first? What is the defining thing of a magnetosphere? And if you haven't thought your hierarchy, take some time to do that, particularly in the field or the domain that you're most interested in now. And hopefully that will carry you on, because all of you are going to be doing something different. If you heard all of the faculty, we all started out doing blah as a graduate student, something else as a postdoc. We're doing something very different now, and we have this career stage. The physics might be the same, the instrument might be the same, the model might be the same, but we're applying it differently. Or we could have switched gears completely. Okay, so what I hope to do in the next 30 minutes or so is to talk about one way to organize all of the plasma universe. So everything that we have in common that we've been talking about is this plasma. And what makes a plasma unique is that it's a charged, made up of charged particles that feel electric and magnetic forces. So magnetic fields, Sarah Gibson's talk on magnetism matters. Why does it matter? Because we're interested in plasmas. And plasmas feel magnetic force fields. And those magnetic fields create the structure of everything. And it also provides the free energy for the things to go boom, right? So if we can understand those big things. We also heard about current sheets. And what I'm going to talk about, we also saw some beautiful pictures of flux tubes and twisted flux ropes. So I'm going to posit that there's essentially 3 structures in plasmas: flux tubes, current sheets, and cavities. And we can organize everything from any scale, from a galactic scale down to a flux tube in the Venus ionosphere based on those. And one of the processes that interacts with all of those scales is this process of reconnection. So we'll focus a lot on reconnection over the next couple hours. And so when you think about the heliophysics and a universal process, I can think about, is there some universal structure? And this is what I'm going to posit for this lecture, there is. And then what are the universal processes that happen in all of those domains? So if I study stellar astrophysics, I can talk to a solar physicist, a magnetospheric physicist in the same language. So think about similarities and differences, compare and contrast, analogies, simple models, and particularly about these structures. So one of the nice things with this framework, there's only a finite number of structures. Unlike if you're a biologist, there are probably thousands upon thousands of species, which you have to figure out the tree of life, where they all came from and how they evolved differently. For space plasma physics, there's just these 3 structures: flux tubes, cavities, and current sheets. So what I'd like you to do, introduce yourself to your neighbor if you haven't yet said hello, though some of you I see are sitting next to people you already know. And see if you can come up with, there's only 3 structures that define the plasma universe. What does that tell us about magnetized plasmas? Can you make a generalization? Can you develop a model? Can you make a prediction? So I'm going to give you 1 minute. So introduce yourself to your neighbor, and what do you think that only 3 tells us about? Okay, everyone, you still guys, you got good interaction going. Does anybody know? I mean, they read the textbook, and actually it's not in the textbook, but well, anybody just know they have an answer? They've thought about this in the past or had a light bulb go off just in thinking about why is there a finite number of universal structures in magnetized plasmas? Everybody know when I say flux tube, what a flux tube is? Current sheet? Why would you have a current sheet only in some place? Okay, thinking about the magnetic field as a force field, as a vector, has a strength and a direction, and that when you bring different domains of magnetic field together, you're going to have some interaction if the fields are parallel or orthogonal or whatnot. Okay, you're going to set up things. Anybody know what Maxwell's equation is the important one for magnetic fields and currents? So you have del dot B equals 0. So you have that there's a closure. What else? Induction equation and Gauss's, Ampere's law, curl B equals mu naught J. All right, so Maxwell's equations are really the physics of plasma physics, right? It's usually one of the things you need to memorize, write it down. And but have you gone through the continuity equation, momentum equation, Maxwell's equations, and figured out what are all the terms? What are the similarities and differences?
What is a cavity exactly in definition?
So I'm going to ask you. So all of these structures, can anybody define a cavity? A plasmasphere? Magnetosphere? Heliosphere? So we have this sphere thing, and what's the boundary of a sphere in Greek? We have atmosphere, cryosphere, lithosphere, biosphere, everything's a sphere, troposphere. What's the boundary? Pause, okay, right? So there's a sphere is a well-defined geometric, a cow is a sphere, right? We have this geometric shape, and inside is one thing, outside is another. So a cavity is excluding something from something else. So a magnetosphere is an example. The heliosphere is an example. What's on the other side of the heliosphere? The heliopause. What has Voyager gone into? Interstellar medium, right? So we have something different on one side or another. We say everything inside is from the sun, solar wind, solar magnetic field. Everything outside is some interstellar plasma, some interstellar magnetic field. And we can scale that, right? We can have a whole bunch of Russian stacking dolls, right? We can have a magnetosphere of Ganymede inside the magnetosphere of Jupiter, inside the magnetosphere of the sun, inside the magnetosphere of our local region, right? And so there's similarities. Obviously, the scales are very different, but we can define similarities. How about current sheets? Where do we have current sheets in the solar system? Okay, so could a current sheet be like a boundary? Oh, so essentially a boundary between different flux tubes. So what defines a flux tube? How can I say this is flux tube A and this is flux tube B? So I can have some type of magnetic shear. So Ampere's law says if I have a shear, a curl of B, I have to have a current. right? So if I have two flux tubes, by definition, I'm going to have some type of current sheet. So at the magnetopause, I have the Chapman-Ferraro currents because I have IMF, the interplanetary magnetic field, all over the place, and my geomagnetic fields pointing north. So by definition, I have to have a current sheet separating those two domains. Right? So I have them all over the place. In the solar wind, I can have a flux tube from an open region right next to a closed region. There's a boundary. There needs to be a current sheet, right? So I have all these things, but of course, what these current sheets are separating are flux tubes. So what I'd like you to do now, again, introduce yourself to a different neighbor, just real quickly. Could you either mathematically write down a formula that defines a flux tube or say it in words? What defines a flux tube? How is it different than a magnetic field line? So you can stay with your neighbor or introduce yourself to a new friend, turn around, or get up. You have 1 minute. Okay, everybody. So for this lecture and for hopefully for a while in your minds, you can think about flux tubes as this smallest element of a magnetized plasma bundle, right? So you need to have something besides the magnetic field. And so just some quick examples and where you can find them in your textbook. We mentioned already magnetospheres and heliospheres. We've already heard examples of planetary current sheets in the outer giant planets. But of course, the sun has a heliospheric current sheet. We have a current sheet in the Earth's magnetosphere. We can have current sheets at the magnetopause. And these flux tubes, these fundamental plasma structures, we saw a whole bunch of pictures, even down into the lab plasma where we had that little spider filaments of this plasma. So nature likes to form itself into these structures. And of course, when you're thinking about a magnetosphere or a heliosphere, all of those three different quanta are going to make up the whole system. And so we can now start thinking about regions. The whole region being the heliosphere cavity. We can think about these current sheets that run along the field lines from one hemisphere to another, right? So Ampere's law says if I have a magnetic field going that way and a magnetic field going that way, I have a curl, and it tells me the direction of the current, and so I have to have a sheet if it's stretched out in a tail-like configuration. And I can think of these individual bundles of plasma having its origin someplace on the sun and coming back as this flux tube. We can disconnect these guys into different structures. So we have these coronal mass ejections and blobs and all types of things. But when you think about a flux tube, what you're really thinking about is there has to be some forces that are defining that structure, right? So when I'm thinking about in a magnetized plasma, I'm thinking essentially about two forces. One is the force due to pressure gradients. So if I have a high density or high temperature region, high pressure region, there's going to be a gradient and there's going to be a force trying to get rid of that high pressure region. Or if it's a low pressure region with a straw, a long straw, you can think about there's forces acting on the straw. But we also have this interaction, this J cross B term, this tension and elasticity of a magnetic flux tube. So a flux tube in this ideal MHD world, so not thinking about particles. And that's another bias that you're going to hear. All of us were trained by different people. Some of us are, I'm from the Jim Dungy Imperial College MHD is everything school. And then there's going to be the University of Washington's Robert Wingley, everything's not a Maxwellian, everything, you have beams all over the place, so how can you think of a fluid? It has to be in a full kinetic mode. But when we're thinking about flux tubes, we're thinking about this ideal MHD fluid description. We're thinking of a bundle of something. We're not thinking of individual protons or oxygen electrons. It's this macroscopic property of the solution. So of course, if we wanted to have a debate, you could say there's obviously more than just three structures. I can go all the way down into particle kinetic structures that can set up all different types of solitons and whatnot. But essentially, we're balancing this right-hand side, this pressure gradient, and the J cross B force. So when you look at that J cross B force, you can expand out J as curl B and do all of your manipulation, and essentially you get two terms. One is the magnetic pressure gradient force, this curl B squared over 2 mu naught, and that looks almost exactly like the pressure gradient force. If I have a high magnetic field area, there's going to be a pressure trying to push things out, or conversely, if I have a cavity, there's going to be a pressure trying to constrict it. But I also have another term here, this tension force. Essentially, is if I twist or stretch or pull on these flux tubes, I'm going to need a force to do that. And so if it wants to go into its equilibrium state, it's going to want to snap back or untwist or whatnot. So I think of flux tubes as these mutually repulsive rubber bands. So you can think of coming out of the sun, you have a whole bunch of rubber bands that can get stretched, twisted, and if you haven't played with the rubber band, you should. Twist one up. What happens to it? You can get all different types of instabilities going on when you think about just long, straight things can get all twisted. And occasionally they can snap, both snap back, like in a substorm or a flare, or actually break apart. So these are these elementary particles of plasma physics. So we've been talking about flux tubes, but generally we have currents flowing along these field lines as well. And so if you just do your Biot-Savart, or you put your thumb in the direction of the current, you're going to make a magnetic field. So if I have a current flowing along a magnetic field, so let's say a magnetic field going across, and I have a current running in that same direction, I'm going to have a magnetic field now wrapping around that magnetic field. And so if I add my magnetic field, I'm going to get this helical structure. So naturally, whenever I have currents flowing, whenever I don't have an equipotential field, when I have these field-aligned currents, I'm going to get these twisted guys. And so often you will see flux ropes and flux tubes used similarly, but you just remember the difference. And you can get these flux ropes in a number of processes. One of them is reconnection, or just shearing the field. And you can move energy from the mechanical motion of the foot tubes into this bundle of magnetic energy that I can then later release. The other skill you need to do here, and we're going to have a lab this afternoon, is we're talking about these things: the current sheet, a flux rope, a magnetopause, There's no picture that I can show you that we've taken from a spacecraft of any of those things. You know, we can say, oh, look, here's a trace photo of a flux tube, and we can see a little twist in the CME. But in general, we're seeing these in situ. So we're looking at a time series, a dBdt, or a dNdt, or dρdt, or dJdt, or something that we've flown through. And so one of the skills to develop is to go from a line plot into a three-dimensional picture in your mind. And unfortunately, we're in the generation where somebody's already thought about this and already have drawn the cartoon. So in the textbooks, we often don't even show the data anymore. We just show the picture. And so when you think about a flux rope, you might be thinking about this picture. But of course, the first people that had a spacecraft fly through, try to figure out what it was, they had to decipher it. So always remember where the picture came from. It could be wrong. It could be analogous to what you're looking, but some other plasma parameters different. How does that difference impact the geometry of your situation? So think about those scales. So we've seen all these pictures of flux ropes and coronal mass ejections coming out. And so I have these three domains, three structures, cavities, current sheets, and flux tubes. What we're really interested in is how do they interact? Why are they the shape they are? What do they do? How do they connect? If I understand one, do I understand something about another? Could I be completely only interested in the global structure of a phenomena and learn something about some of the smaller scale physics, or vice versa? What separates them? We have all these names: the plasmasphere, the plasma sheet, the current sheet, the Chapman-Ferraro currents, flux tubes, polar wind, solar wind, coronal mass ejection. We heard CIRs, all different types of. What defines them? Is it a different combination of flux tubes, a definition of current sheets? Is it in one region or another? And can we actually have the sun influence the planets? We'll talk a lot more about this after the break, but magnetic reconnection is really the fundamental process of space plasma physics. So if you think of the three domains, this is the process. Of course, there's lots of other processes that are important, but one of the things in this model of flux tubes and current sheets and cavities is this is the process that connects them. When I bring a flux tube from one domain into contact with a flux tube of another domain, how can they interact? If they're mutually exclusive rubber bands, they should just bend around each other and pass over or through. Reconnection allows them to intermix their plasma. So I can have a plasma that has coronal type properties intermixing with a closed field line region. Or I can have an IMF flux tube interact with a magnetospheric flux tube. And then the resultant plasma is going to be very different. I get this intermixing. So reconnection essentially breaks this topology, or breaks these flux ropes across current sheets. So we'll see if this works. So this is, I think, an NRL old animation of what we've been looking at, essentially this eruption. We're looking at the sun and this big material. You'll see that the colors are velocities, and you had interactions between something down below and then something on the top, and it has this twisted domain structure. So we had reconnection happening at two places in this event. One down here at the feet, where we have oppositely directed flux tubes are able to reconnect or disconnect. And then we also had to have reconnection on the overlaying field lines, so it could escape this closed field region. And you have this coronal mass ejection expand out. So we also in the last 5 years or so, Taifan has been using the wind data that has very high time resolution plasma data. He and Jack Gosling have been looking at signatures of reconnection, essentially jets of plasma as you cross a current sheet. And so not only do we have what looks like reconnection on the sun in different places in the solar atmosphere, but even across the heliospheric current sheet, you can get shear. I can have a magnetic field line in a different direction. And they found shears of just a few degrees. We always think of anti-parallel fields. They found shears of just a few degrees can give rise to reconnection events. So where would we have reconnections? At current sheets that define shears. And those current sheets don't have to be very large. And of course, so Jim Dungy just passed away this year, and he was given a problem by Fred Hoyle. A solar physicist was thinking about where flares come from and reconnection. And Hoyle asked Dungy, could this be happening here on Earth? So we developed this open magnetosphere model where you had reconnection on the day side and reconnection on the night side, or magnetic merging on the day side and reconnection on the back side. We've lost that difference now between merging and reconnection. We just call it all the same thing. But you sort of think of this cycling. You get this disconnect on the day side, and then it comes across on the night sides and reconnects and starts again. And he had a hard time publishing all this idea, but now explains most of the global behavior of the magnetosphere. Many groups have developed global MHD models that, of course, can't look at the physics of reconnection at the scales that matter, but they can look at some effects with anomalous resistivity or numerical resistivity and explain a lot of the observations that we see in situ. So we form structures, these plasmoids or flux ropes in the magnetotail. And one of my favorite pictures, it's been almost 10 years now, Mark Morris at UCLA, looking at the center of the Milky Way, had an image of this Helix Nebula. You can look at what it's made out of in terms of magnetic fields. This is a flux rope that has the dimensions of 80 light years. Right? So when you think of a flux rope and you think about from Venus to the sun, to the magnetosphere, to a galactic center, the same type of structure happens. You get this twisting because you can now infer there must be some type of field-aligned currents. There must be some global magnetic field that has different pressure gradients across it, both either magnetic or plasma pressure that give rise to the structure. So, take-home message. Think about how you organize your thoughts. Think about your biases, and not only your gender biases and wherever you grew up biases, but also your training biases. If you're a physicist, you have a bias. You were trained to look at things to simplify. And so if you're going to go into astrobiology and start thinking about exoplanets and habitable zones, you're going to be working with people that had a very different thought process in terms of a tree of life complexity and trying to divide things up into finer and finer things instead of trying to get them down to, the grand unified theory. And you'll approach problems differently. For us, as you showed, almost all of us are physicists. So we have the same common language. And so if you're thinking about a reductionist approach, look at your problem. Can you identify what is the domain of your problem? Are you a heliophysicist, a magnetospheric atmosphere? Are you just a mesoscale convective complex looking at sprites or jets? What's your domain? What defines that domain? How do I know I'm outside of that domain? Where would I draw boxes from other domains into my domain, and where do I draw boxes out? And so that's one of the purposes of LWS, is to jump into the domain of societal relevance. Who cares that there's an 80 light year long helix nebula that's evidence of a magnetic flux rope. Does that tell us anything universal that we can describe about us? After the break, we're going to spend a lot more time talking about reconnection. And what I'm going to try to do is simplify reconnection so you're thinking about scales. So that's the other universal process. And if I'm on your PhD dissertation exam committee, that's the first question I always ask. What are the scales of your problem? What's the temporal scale? What's the spatial scale? And then how does that allow you to throw out this term, or in this Reynolds number domain, or whatever you're doing? So think about scales. And we'll talk about reconnections shortly. Great. And I say I did it in 42.5 minutes, but my watch says it was 47. Questions? There is a quiz, and I'm not joking. Sure. So these are radial velocities, so a negative velocity is back towards the sun.
It's still probably moving outward, right?
Sure. How many of you have all of you passed your qualifying exam? Okay. So that's one of the most stressful periods of your life in the last few years, was the qualifying exam, because there's not a lot of make or break events. You know, if you're an Olympic athlete, okay, this is it. But for most people, it's not a make or break. And I've seen people's thought processes go all over the place. I've had students actually pass out. It is really stressful. But when I have people have the solar wind going back towards the sun, they're not thinking right. But here, I can have a negative radial velocity, but I could still have an outward velocity. How would I do that? What frame of reference am I in? So if I'm an expanding CME, and I'm one side of it, if you look at the velocity profile of a CME at 1 AU, it has this declining profile. At the front end, it's going faster than the back end. And you can imagine that if I have a CME that's expanding as it goes over me, I'm first seeing the leading edge in the same direction of the solar wind, so it seems fast. But when I get to the back, it's expanding away. So I have this combination. So reference frame is huge. So where are you? In which reference frame? The picture that Janet showed freaked me out, of the planets orbiting with Mars in retrograde until I figured out, okay, it's a fixed Earth-Sun. But you have to always figure out your reference. Carl?
You're thinking in terms of sheets, cavities, tubes. On the solar side, we're thinking of nulls and spines and fans. How do they complement your?
What's a fan?
Fan plane is a set of field lines that comes out of the null. And it's basically a separator of the luminar conductivity.
Yeah, I'm sure there has to be an analogy between the current sheets, but when you think about any plasma domain, if they have a different source region, they're going to have some type of boundary. It's going to be a hotter plasma or colder plasma. It's going to have more twist or less twist. And so I'm not sure of how I would map a null and a fan, but there probably is a current sheet.
Partition thinking in domains of conductivity.
Okay.
And see nulls as sites of
And probably that entire schematic and design was based on some type of observation. Is it magnetograms or is it?
It comes out particularly about the way you think about pure potential, generalized.
Okay.
But do you think there is application in a sense? I think that to think about nodes and spines is very powerful for a specific application of exactly finding those points where the whole structure can very quickly change topology, right? And I think that it's equally valid, right? Do you think about the magnetic, do you think about these things in terms of currents or magnetic fields, right? We generally, using the magnetic field, just focusing on the currents will be enough to describe the thing. Focusing on the magnetic field also is sufficient, but then one is easier for us to grasp, or one is more useful for a specific application. And so I think that it's just they're just the same. And ultimately, you're dividing space in domains. Right?
So they're not the same. They're complementary, but you didn't mention them.
Right.
But they serve the same function. Partition the volume you're trying to think about into substructures that enable you to follow processes from one to the other. And it's not just a different set of words, it's a different set of applications.
Yeah, and that's hopefully a point too. All of us have come in with our own conceptual framework of how things work, and that's usually how you were taught. It will change over the course of your career, but if you don't recognize early that there's more than one way to think about your problem, you're going to be in a lot of arguments. And a lot of them you're arguing from different conceptual frameworks and using different words, but really you agree, but it's just a different conceptual framework. So be multilingual, think about it in terms of different scale sizes, kinetics, plasmas. Janet?
I'm going to criticize also.
Okay.
You're showing and discussing a picture that's magnetic field on,
Right.
but there are other regimes that are equally broad and applicable for the Heliophysics domain. For example, in the solar wind, you can have twists by virtue of velocity because you're in a frozen-in situation. The fluid is controlling what the magnetic field does. One could have a vortical motion in the fluid that gives up. And likewise, you're ignoring the presence of neutrals and their potential influence in some domains. When you get into rubber atmospheres, you have to worry about the fact that there's collisional coupling
Yep.
at some level between neutrals and ions that can also influence in a very important way what's going on, including reconnection.
I'm neglecting all chemistry.
So this is a purely, this is a very formal kind of picture.
So I build magnetometers, and if I showed you a data sheet, I would call it a current sheet, where if you're a plasma instrument, you'd say you just went through the plasma sheet. And that's where the names came from. If you were a plasma instrument builder, and you saw this gradient in plasma pressure, I define it as a plasma sheet. But if I'm a magnetometer and I see my magnetic field flip, like Nick showed, I'm going to call that a current sheet, because that's a definite. So it's the same thing. And then we can say, well, actually, the current sheet's a narrow part. The plasma sheet can be much broader in terms of scale lengths and whatnot. But it's essentially the same dividing line. So remember your biases. So if you're going to have an ideal MHD view of the world, it doesn't work everywhere. Right? And there are a lot of times when you have to start thinking about chemistry in the upper atmosphere of the Earth, or neutral winds giving rise to a dynamo that impacts your electrodynamics. So even though you think of it as a plasma E and B thing, I can have neutrals running around giving rise to very important differences than if I neglected it. But the way we usually solve problems is try to grasp it. We are, with the advent of faster and faster computers, we're able to do much more global coupled models. So we can start throwing in different physics. But I bet none of you, as part of your career, will develop a global coupled model. You'll probably work on them and maybe contribute a new PIC module into an MHD module where you start getting across scales. But you need to have the expertise of an electrical engineer and a computer science and a numericist and a physicist and a chemist, right? So you're going to be working on teams, talking different languages. Remember your conceptual framework when you go in, and try to learn from who you're working with, because not every problem does a hammer fit. Break.